yes, I'm continuing right along where we left off here. And I want to get into complex numbers and the Born interpretation of the wave function. Okay, first, let's talk about complex numbers. Okay, so if I use the number, I'm going to use the letter, excuse me, z to symbolize my complex number. And a complex number is made up of a real component and an imaginary component. Okay, so the real component I'll symbolize with the letter x. And often we will see the symbol RE to denote that that's the real component. And then there is the imaginary component, which is going to be imaginary number I. And it could be, multiplied by number y as well. Okay, and so this makes up my imaginary component. Okay, and then we also will have the complex conjugate that we denote as z star. And the complex conjugate is written as x minus iy. Okay? And when we multiply, so let me write that down. I'll just abbreviate and call that the conjugate. Okay? The complex conjugate. And when we multiply the complex number by its corresponding conjugate, we get what we call the square modulus. And I can represent that by saying z times z star, which symbolically we would write that as like this, z squared, the square outside of those absolute value brackets, okay? And if these are my two, if this is z and this is z star, through the process of FOIL, right? So I'll say hint FOIL, first, outside, inside, last. Then if I multiplied these two things together, I would get, so the first is x squared, okay? First, the outside is going to be minus iyx. The inside is going to be positive iyx. And so all of that will cancel. And the last will be iy times negative iy. And that is going to give me positive y squared. So when I take the square modulus, I get a real number, okay? That's what's important to denote here. And so we can have wave functions that are described by complex numbers. That's not an issue. However, to extract useful information out of our wave function, if it's made up of a complex number, we really need to be in the realm of real numbers to get our eigenvalue. So in the Born interpretation of a wave function, we use the square modulus, and the square modulus represents a probability distribution, okay? Or as the figure says, a probability density, okay? So I'm just going to demonstrate really quick with Mathematica complex numbers. And instead of using x's and y's, I'm just going to use real numbers so I can get an easy result. I don't have to use a function that way. And I'm just going to say z equals 2 plus 4 space escape, I escape. So there is my complex number, shift enter, there we go, 2 plus 4i, okay? I can ask Mathematica to list for me the real component and the imaginary component by saying, and I'm going to do that as a list, so I'm going to say RE bracket Z in bracket. That'll give me the real portion of the complex number, comma, and then IM bracket Z in bracket squiggly, and that'll give me the imaginary component. And when I do that, yep, 2 and 4. 2 is the real component, 4i is the imaginary component. Okay? So if I now, I'll just demonstrate here where the square modulus, we think we can just square z, for example. if I just take z squared, notice here, I get an imaginary number, negative 12 and 16i. And what that operation just did, z squared, it FOILed 2 plus 4i times the quantity 2 plus 4i. But that's not what the square modulus is, okay? This is what the square modulus is. It's z, and I'm going to say space z for times. And in Mathematica, I can go escape, conj, escape, and look at that. It looks just like my lecture notes with that little star. That little star there means conjugate, complex conjugate, okay? And then now if I do that, look, I get a real number. And so in case you can't FOIL this quickly in your heads, I will demonstrate to you that if I say 2 plus 4i, okay, multiplied by 2 minus 4i, because 2 minus 4i, right, is going to give me the complex conjugate, that gives me 20, okay? So that's the math, that's the complex numbers. What does it mean for the wave function? Okay. Well, much like in the intensity of light, so if you square the amplitude of a wave, it gives you light intensity. So the Max Born, famous quantum mechanicist of the golden age, right? He was part of that group in the 1920s with Schrodinger, Heisenberg, and Einstein, and so on. He interpreted that if we take the square modulus of the wave function, this will be a probability density. So for example, if I have my wave function psi, notice here that I get positive values, okay? So I'll say on this coordinate, right, we've got positive values on this side, but then negative values on that side. So, right, this looks, it's a sine wave or a cosine wave, if you will, okay? And then notice in the probability density here, which is showing you this red curve, as well as this kind of shaded region, that is the square modulus, which is psi times psi star. And what we notice here is whether we're looking at the wave function or the probability density, we see maximum in the same place. But now, of course, this is the negative region of the wave function, right? And so the way we interpret that, where this probability density, or even where the wave function peaks, that's going to be the most likely position to find this particle. So in other words, my x scale here is position. It's the location of this particle along some finite axis, right, on the x scale. So the probability density gives me real numbers, real positive numbers. And as it turns out, that's what we want to work with in terms of wave functions when we want to get the eigenvalue out of the wave function, such as the energy. Okay? And so what that means is when we go to compute the square modulus, okay, I'm going to write it. So I realized just now I've been writing it backwards. Typically, we're going to see this as psi star psi. Okay, so let me, just to make sure we're on the same page here, because this is going to be one of these subtleties in math where the order is important. Okay, so we're always going to see this as psi star psi. All right, that equals my square modulus. Okay, and if I want to now extract useful information out of this, such as taking the area under the curve, right? Then what I want to consider is the following: square modulus times dx, okay? But what if we get into something more complicated? So this is one-dimensional, right? What if we want to do three-dimensional, which is really what we want to do, right? We want to be able to talk about things in 3D, okay? So then what we would do is say psi squared dx by dy by dz, and that would give me my 3 dimensions. And of course, as you might guess, we would be putting a triple integral on the sucker, all right? Well, as it also turns out, the Cartesian coordinate system isn't very useful in quantum mechanics, or really in physics. Polar spherical coordinates are what's far more useful because we can describe a radius and angles about some point of origin. So I'm going to modify my dx, dy, dz, okay? And we're going to say square modulus times d tau, all right? And so d tau is my three-dimensional representation. And we typically use d tau in our polar spherical chords. Parent life. Okay, moving on. Wait, let's see here. What did I do? Oh, yes. Okay, so we're going to get back to that d tau polar spherical coordinates in one moment. But continuing along on this Born interpretation, okay, that the square modulus gives me the probability distribution, which for now it tells us what could be the most likely place of finding a particle along some axis, okay? So if psi is a solution to the Schrodinger equation, then so is n times psi, all right? And n is a proportionality constant that makes the Born interpretation an equality. So in other words, the Born interpretation just says that the square modulus is proportional to the probability density. We have to normalize the wave function in order to make that a definite equality. And so here's our mathematical operation to carry that out, all right? N is my normalization constant, okay? And because I have square modulus psi star psi, right, what I really have going on here is n times psi star and n times psi. So that would represent a normalized wave function. Both of these would be normalized, okay? And if I integrate over all space, that equals 1.0. And the way that we can interpret that, the way that Born interpret that, is when we have a normalized wave function, this 1, what that means is 100% chance of finding the particle between negative infinity and positive infinity. So we're casting a really big window. We're basically saying that once we normalize the wave function and we integrate the square modulus over this very large range, there will be a 100% chance that we find the particle in that range, okay? And so as you might guess, because n is a constant, it can come out of the integrand, and so that's where we get the n squared, okay? So we can find the normalization constant by saying n equals 1 divided by the integral, and I'm just going to replace psi star psi with the square modulus dx, and of course this would all be square root. And of course I could take the square root of 1, you take the square root of both sides, but we know that that's equal to 1, okay? So when this condition is satisfied, we call this square integrable. So the wave function is square integrable, okay? So, but now what if we were doing this in 3 dimensions, okay? So I'm gonna write, if we have normalized the wave function, I'm gonna write that as psi sub n, and so we can think of that as being my normalization constant times psi. So when I write psi sub n here, I'm talking about a normalized wave function, okay? So if I was doing this in 3 dimensions, as I discussed, right, we would have to do the triple integral, and I'm just gonna write all from negative infinity to infinity for the square modulus, and of course that would be dx by dy by dz, and that would all equal 1. Okay? So, and of course, we could find the square modulus in the same way, or excuse me, find the normalization constant. If we had dx, dy, dz, right, it would still be an n squared out in front. Okay, and all of that equals 1. But now if we had polar spherical coordinates, right, we would want to look at this in terms of the following: psi, the normalized wave function, square modulus, and d tau, and all of that will still equal 1. So how do we convert that Cartesian coordinate into a polar spherical coordinate? Okay, well, recall this thing. D tau equals r squared sine theta dr d theta d phi. Okay, I'm not going to go through and prove this mathematically, but I am just going to remind you of a couple things where this d tau comes from. So for one, when we're converting a Cartesian coordinate system to a polar spherical coordinate system, we note that x will equal r sine theta times cosine phi. And here you can see my coordinate, right? X, y, z. And phi gives me the equatorial region, and theta gives me from pole to pole. Okay, so in this case, r tends from 0 to infinity. So in the xyz scheme, that's negative infinity to infinity. But remember, my radius is starting right there at the point of origin, 0 to infinity. Okay. My theta dimension goes from 0 to pi. That's a 0, not another theta. And phi goes from 0 to 2 pi. Okay? And so I will just kind of draw a slightly better picture. They're showing you where this r squared sine theta dr d theta d phi comes from. But I like to draw this picture. So if I put my point of origin right here, okay, and I draw out a solid angle, okay, that's what this is. And this will be amazing if I can draw this solid angle with my tablet thingy here. Oh, it's going really well so far, you guys. I'm feeling really good about this. I can't write for a damn with this thing, but apparently I can draw solid angles. Okay, lovely. So this thing, I'm going to shade it, and this is my, so this represents a volume element that I might be interested in, okay? Like what this shows right here. And if this is my radius, right, okay, then remember, theta gives me my equatorial. So this angle represents d theta. Theta gives me my pole to pole. Phi gives me my equatorial. So that means this angle right here gives me my d theta. And the thickness of this slice gives me my dr. And now I'm not going to go through this, but through SOHCAHTOA, we would then come up with that this side right here is r sine theta d phi. The thickness is dr, okay? And then this side is r d theta. And so if I want to know the volume, and really remember the volume of this thing represents d tau, okay? So then volume is length times width times height, okay? So that's where I get all of these multiplied to result in r squared sine theta dr d theta d phi. So let's see what's next. So what that means, okay? When we write the following, if I want to normalize my wave function, and I want to normalize it in polar spherical coordinates, which is exactly what we're going to do. You're going to do this in Mathematica, okay? And I also encourage you to be able to attempt to set it up by hand. Of course, solving these integrals, you know, we have Mathematica to do that for us. So, but what we would do, we would say the following: n squared, okay? And my first integral goes from 0 to infinity. That's my r. My second integral goes from 0 to pi. That's my theta. And my third integral goes from 0 to 2 pi, which is phi. All right. So then I would have square modulus, which we recognize, remember, that's psi star psi. Okay. And I also want to point out that not all wave functions will necessarily have imaginary numbers. Okay. Sometimes they will, sometimes they won't. And we'll cross that line when we get there, which I think will be very soon. So now when I write d tau right here, I have to replace it with this whole thing. So I have to also say r squared sine theta dr d theta d phi. And this whole chunk will be equal to 1 to normalize it. So for example, if I have r's or sine thetas in my wave function, those will get absorbed. So I might have like an r cubed or a sine of theta squared if I also have those terms in there. Okay. So this is where students historically get, you know, kind of lost. So we're going to do this in Mathematica. We're going to work on solving problems like this. But what I want you to recognize, if we see d tau, we have to replace d tau with r squared sine theta dr d theta d phi and carry out the triple integral. Okay, we'll get there soon. So moving along. So now, in continuing with the Born interpretation of a wave function, because the square modulus gives us a probability distribution, we also have to recognize that psi, the wave function, is going to have some constraints. It can be made up of imaginary numbers. However, it also has to fit some other guidelines. So for example, a wave function has to be continuous. A wave function also has to be single valued. It has to have a continuous slope, all right? And it has to be square integrable, like we were talking about. It has to be able to be normalized, excuse me, okay? So I've got some pictures right here that says, are these wave functions acceptable? And if we look at this, okay, A, think about it for a second. It's unacceptable because this is not continuous, okay? So that makes it not an acceptable wave function. Okay, what's wrong with B? So B has a discontinuous slope. What's wrong with C? It's not single valued. And what's wrong with D? It is infinite over a finite region. So no, none of these wave functions are acceptable. Okay? So carrying on. So now when we get to the Schrodinger equation here, okay, so I'm kind of shifting gears here, and I'm going to talk about how we solve this thing. So I mentioned already, I just kind of showed you the solution to this thing. These are second order differential equations that have standard solutions. Oops, my Mac controls are going, there we go, okay. So I'm going to set this up here on how we begin to solve it. And then I'm going to record just a separate, very quick video that's how to solve second order differential equations. So more largely a math lecture, okay? So when we look at this form of the equation, this is a standard diffie-q. So I'm going to say standard second order, diffie-q. And the form of that is the following, okay? Second derivative of y with respect to x plus some constant times the first derivative with respect to x plus some other constant times y equals some function r of x. So basically, if you're looking at this and you want to make comparisons to a polynomial, right? Something that we would apply to the quadratic equation. That's exactly what we have going on here. We put these types of equations in a standard form, just like we put a square polynomial into a standard form so that we can use, in the case of the polynomial, we can use the quadratic formula. In the case of these differential equations, we put these in these standard forms because they also have a standard solution. And so when we put this into what I will call the reduced form, the reduced form sets the right-hand side equal to 0. So plus by equal to 0, okay? So I'll write reduced form, okay? And so now there is a procedure to solving something of this form. And I'm gonna record a separate shorter video to go through that and to show you where we get this solution, okay? Or we'll show you how we get the solution. And along with that, I'm gonna give you some examples, some practice examples. And I think I'm gonna put those practice examples in Canvas with just the answers that if you want to, you can practice using it to make sure you see how this goes, okay? Okay, folks, yep, so I've got about 28 minutes that I've been talking. So I'll see you in the next video.